So jumping right in, my name is Elena McHale, and I will be presenting a lightweight transformational approach to support large-scale adaptive changes. This was written by Michael L. Collard, Jonathan I. Malatek, and Brian P. Robinson. The paper was written for the 11th IEEE International Conference on Software Maintenance in September of 2010. It has 75 paper citations. Michael L. Collard is an associate professor of computer science at the University of Akron. His interests are in software engineering, software evolution, software maintenance, and computer science. He has an age index of 24. Malatek is a professor of computer science at Kent State University. His interests are in software engineering, software evolution, software maintenance, and computer science. And he has an H index of 41. Robinson leads ABB's global software improvement activities and is their designated technical expert. He is interested in program testing, regression analysis, program slicing, and the C++ language. I couldn't find an H index or photo of him because his name is so popular, so many photos came up, and I couldn't find him on Google Scholar. The main research question for this paper includes, is there a better way to undergo system modification without relying on manual manipulation? Another question we can ask off that is, how much more successful would this alternative method be in compared to a manual manipulation? The motivation for writing this paper stems from the developers easily making mistakes when manually undergoing modification to address changes in software. So in large-scale changes, there can be a lot of time spent on adapting code, and they may even miss parts due to human errors. So a lot of the time they'll choose to postpone adaptation, and due to those reasons, they might miss out on new features and technologies, and that can just hinder them further. The research in this paper is in regard to a lightweight transformational automatic approach to adaptive changes using SRCML toolkit. So SRCML toolkit was selected because it is programmer-centric, robust in working with incomplete code, has different compiler versions, and is a partially mitigated source code. It is also an XML format, which can be used to augment source code to add explicit structure to program source code. Some of the benefits to SRCML include its ability to represent code that is unable to be compiled, its efficient speed, its lack of base on a particular compiler, its use of XML tools, and the use of XPath extension functions. Now let's get into some transformation examples using SRCML. The first affects the new operator. It used to return null for memory error, but it was changed to showing an exception instead. Looking at the code on the right, the new operator must be identified. The expression that calls the new must be isolated in the try block, and or I should say try catch block, and the result must be tied to the original statement. The second is a change in the compiler where default must now be explicitly stated. By using the transformation on the right, we were able to identify unspecialized classes, prevent false positives, and handle multiple template parameters. The third one I have on here is the scope of variable declaration in for statements that was originally in an enclosed block is now being changed to where you can put it outside of a block. To do this, they matched all occurrences of the iterator variable declarations that needed to be moved, rearranged statements that involve multiple templates, and created an extension function that can perform one template. All right, so the fourth is a change that prevents buffer overruns. Through this transformation, you can successfully identify calls to a specific function and construct a new call based on the original call. The second one that's on this slide, or the fifth one overall, changes runtime frameworks that cause errors to occur where they typically didn't before. The transformation identified expressions where invalid references to vector data are used. So finally, this one's kind of unique. A transformation was needed to be performed because in some cases, compiler mitigation is performed and not fully prefixed. This was difficult for the lightweight approach to address because it wasn't possible for this approach to determine if a variable was a function pointer. So with that being said, a function needed to be written for each function, or I should say a transformation needed to be written for each specific function. The transformation was used mainly as like a search and replace tool with some context knowledge. So the goal of the case studies were to compare the manual approach with the automatic approach. The first study contained 122 kilo lines of code in 405 files. The code was composed of procedural and object-oriented code. The change being made in this case was a new standard for throwing a memory exception instead of null. Of the 479 manual adaptive maintenance changes that were made to accommodate the compiler update, 40 of the cases were missed with a manual change, and all changes were made correctly by an automatic approach, which is quite a difference. The second case study. So there were around 3.9 million lines of code in 13,800 source files in this case. They were comprised of object-oriented C++ code and procedural C code. So developers manually made 1,756 adaptive maintenance changes on a compiler that underwent mitigation or migration changes. Only 2 mistakes were made in the automatic approach, and this was due to the first being imprecise code pattern matching, and the second was due to a need for a requirement for a more precise type resolution. However, on the other side, the manual approach actually missed 304 changes, so you can definitely see a difference between 2 and 304. And I also have the table to the right here so that you can see their findings in a more visual presentation there. So, in conclusion, based on their research, this shows that the lightweight automatic transformation approach worked better than manual changes. This can be beneficial for compiler migration and other adaptive maintenance tasks in the future. So some future work that could be made is correcting old work that was once done manually in the past, and overall just making it run better. And the second thing we could do would be to create a resource that has functions for common maintenance transformations, and this would be good for saving time in industries when they can look up that almost library of functions. So in conclusion, I really liked how the paper presented their research. It was very complete with a lot of benefit that seemed to come from it. This definitely could be practical for developers. Another thing is I think a lot of developers are looking to save time, especially on things that are just maintenance changes. I don't think a lot of developers want to spend all their day working on something when they have other time commitments for other projects. So I am interested to see your perspectives in the discussion and address any questions you might have.